Hello. In this episode, I would like to talk about more examples on the application of L'Hopital rule. In this set of exercise that we should not be limited to only using L'Hopital rule because sometimes other methods may apply or may apply even better. So in the textbook, title of this group of exercise is as follows. Okay, so I'm gonna type it, right? Examples on L'Hopital rule, when where appropriate, okay, if there is a more elementary method, consider using it. And sometimes the L'Hopital rule may not apply, right? If the L'Hopital rule does not apply, you may like to know why, right? So let's first review what is the content of L'Hopital rule. L'Hopital rule basically says if we take limits of a function in quotient form, right, f divided by g, then the limit of this quotient is equal to the limit of the quotient of their respective derivatives, okay? But this is, of course, is a conditional. So it's either both approaches, the numerator and denominator both approaches zero, or both approaches infinity. So there are just these two cases. Well, there are actually, you say, two major cases. So either f of x and g of x approaches infinity, or they both approach zero. Okay. And if one approaches zero, the other one does not, then we cannot apply L'Hopital rule. So let's look at first example. Okay, so I'm gonna make this example number one. Okay, we may remove some examples I prepared because I try to try to control the amount of time we spend on this recording. Okay. I prepared a lot of examples. Okay. So the first one, okay. The first one we have, so I'm gonna bring the L'Hopital rule underneath. Okay, I'm gonna bring L'Hopital beneath it. So it's always follows us. All right. So on this first example, and then we first need to, so number one, we want to know how to, whether the question, is fitting to apply L'Hopital rule. Secondly, is how do we express it? How do we express it? Okay, so I'm going to show you how to express it. So on this piece of paper, right? Ideally, if I can divide it in two parts, but that's going to be too much hustle, okay? Because this is just one page. So what I'm going to do is I'm going to have a scratch paper, okay? Scratch paper. So think out aloud. So think out aloud for me is just the area for the use of scratch paper. Okay, so scratch paper is something you don't have to show, but you want to keep it to yourself. And you should always study with a piece of scratch paper. If at this moment you want to try by yourself, and feel free to do that. You can pause or you just stop it and come back if you wish. Okay. So first of all, how do we move on to the next step? So when we check the condition, you actually don't need to check the condition along with your work. Okay. you would say, okay, it equals to, so on your scratch paper, you check the condition to check, okay? If the numerator approaches 0, right? And remember, this is and, right? And, or they both approach infinity, right? Or the denominator, what does the denominator approach to? Okay, denominator is x minus 1. All right? So when x is approaching 1, ln x is continuous at 1. Okay, ln x, the domain is x greater than 0. So by the continuity properties, logarithm function is continuous in its domain. The domain is x greater than 0. 1 is in the domain. Therefore, this is just a direct substitution, ln 1. ln 1 is equal to 0. And in the second case, and in the denominator, when x approaching 1, it's a direct substitution because x minus 1 is a polynomial. So it's a 1 minus 1 equals to 0. So we have this limit approaching 0, numerator's limit approaching 0, denominator's limit approaching 0. So we can apply L'Hopital rule. And of course, g of x is not equal to 0, in the neighborhood of 1. That certainly is true, okay? So when you show your work, this is how you show your work, okay? This is how you show your work. You show your work by still have the limit, okay? You still have the limit, and you take a derivative of the numerator, okay? So now you have decided that it applies, so you take a derivative of the numerator. This is not an application of a quotient rule. So please do not use a quotient rule. Quotient rule does not apply here. All right? Quotient rule does not apply here. It's derivative of the numerator divided by the new derivative of the denominator. It's two separate derivatives. So the derivative of numerator is 1 over x. The derivative of x minus 1 is equals to 1. So when you show your work, don't put these in between the lines. You just put here, you just put a 1 over x, and the next one is 1. So then you say, how does your reader, especially how does your professor read this? Well, your professor read it, and usually, and he or she can tell, okay, this is derivative and this is derivative. Can we use the L'Hopital rule? And yes, we can. So the reader will check the condition, and I can see whether you have checked the condition. Okay, so don't put these things in between the lines. Okay. So now we got this 1 over x divided by 1 is just 1 over x, right? And this will be a direct substitution because 1 over x as a function is continuous at 1. It's a rational function continuous in its domain. So it's 1 over 1 equals to 1. So this is how you show your work. So be careful. Be careful. Okay, I'm going to put a specific note here. Please do not use quotient rule. If you use quotient rule, it's completely wrong. Okay, it's completely wrong. So it is the derivative of the numerator, okay, and the derivative of the denominator done separately, not quotient rule. Okay, and this question is done. This question is done. Okay, so let's look at the second question. Okay, second question. Example number 2. And of course, most likely we might be using L'Hopital rule, but sometimes we may have to use some other methods, right? If L'Hopital rule does not apply. This is the case that when x is approaching infinity, so once again, we're going to think out aloud. My scratch paper, okay? Then you just take a derivative, you're checking, but your reader doesn't need to see this. Okay, you're checking and say, I'm writing this down. Is this I'm checking in my mind? Okay, so this is infinity, right? And when x approaching infinity, x squared approaches infinity. So this approaches infinity. So obviously, L'Hopital rule applies. L'Hopital rule applies. So we're going to take derivative on the top separately from the derivative of the denominator, okay? So when you show your work in here, oops, sorry. All you have to do is just, you're gonna write equals to, okay? As x approaching infinity, the derivative of the numerator is e to the power x. The derivative of the denominator is 2x, and we can actually apply L'Hopital rule one more time, right? Because it still is true. And then you're gonna, the derivative e to the power x is still e to the power x. The derivative of 2x is 2. And now look at the derivative of this, whatever is left. Well, x approaching infinity, this is going to be infinity. All right? Okay. So that's question number 2. So the amount of work you have to show is just this much. You don't need to show all of these. Okay, if you really, really want to show, okay, put it on the side. Have a little space here and show your work, right? If you really, really have to do it. Okay, if you really, really have to do it, it's just do it on the side. You make some space on the side on your paper and then you show your work. All right? Okay. So that's about how to show work. Okay. Next, let's look at example number 3. Okay. By this time, I'm going to, in some cases, I'm just going to say it, right? We're going to take a derivative, we're going to take limit as x approaching infinity, this particular situation. We have a numerator, we have a denominator. When x approaching infinity, ln x approaches infinity for sure. X approaching infinity, root x approaching infinity. So we have an infinity over infinity case. So we can take derivative. See, this time I'm not even using any scratch paper. I'm just going to take a derivative like that. And the derivative of root x is 1 over 2 times root x. We're going to simplify this. Okay, we're going to simplify this. How do we simplify this? We have root x in the bottom. We have 1 over x. So we're going to multiply the common denominator. Okay, the common denominator will be x, right? So we're going to multiply x in the top, multiply x in the bottom. And then we got the following. X times 1 over x, that's going to be equals to 1. 1 over 2, this 2 actually will flip up, okay? So x times 1 over root x, and that's just going to be root x in the bottom, okay? So this is gone. And then you say, how about the 2? Well, the 2 actually flips up, okay? The 2 actually flips up, Okay, so the denominator is just the root x. While x is approaching infinity, numerator is a fixed number, denominator approaches the infinity, so the limit is going to be a 0. Okay, so that's done. So that's the example number 3. Let's look at example number 4. Okay, and we're going to put this L'Hopital rule under. Okay, now what do we have here? Well, x is approaching 0. Tangent approaches 0. X is approaching 0. So the top is 0 minus 0. The denominator is approaching 0. So the top is approaching 0. Denominator approaching 0. So we have the first case satisfied. First case satisfied. Okay, so we can just use L'Hopital rule right now for the first step. Okay, and we're going to take a derivative of the numerator separately. Okay, so secant squared of x minus 1. And the derivative of the denominator, x to the power 3, is going to be 3 times x squared. So by this time, right, what do we do? What do we do next? What do we do next? And if you look at when x is approaching 0, denominator still approaching 0. Numerator secant x, when x approaching 0, secant is 1 over cosine. This is approaching 1. Excuse me, 1 minus 1 is still approaching 0. So you could take a derivative again. We actually could take a derivative again. If we we can still apply L'Hopital rule. Okay, we can still apply L'Hopital rule. So let's try it. Let's try it. Okay. We can still apply L'Hopital rule. So we're going to apply L'Hopital rule the second time. And the derivative of the denominator is going to be 6x. And the derivative of the numerator, okay, we're going to apply chain rule. The derivative of secant squared is 2 times secant x, and the derivative of secant x is secant x multiply tangent x. Am I right? Let's double check. I hope you can pause and double check, and I think I have checked. This should work, right? This should work. And what do we get? Let's see what we get. Okay. We're going to simplify this. We got 6x, 6x, and 6 and 2 would reduce, right? So we got 3 in the denominator. Secant x times secant x, that's secant squared, and we have tangent x. And this time we can do secant squared, right? Because secant x times secant x is secant squared. Secant squared times tangent x. When x is approaching 0, the numerator still approaches 0, the denominator still approaches 0. You can certainly apply L'Hopital rule one more time, but remember, your numerator's derivative gets a little bit more complicated, okay? It gets a little bit more complicated. So I'm going to take a different route. Okay? Tangent x is equal to sine x over cosine x. Okay? And what do we get now? Is that because 1 over cosine, right? We're going to write it this way. Sine x, I write sine x on the side. 1 over cosine x, that's a secant x. So we got secant x to the power 3, right? So we got secant x to the power 3. and sine x. Okay. So I think some of you might have guessed where I'm heading. I'm going to bring sine x over x. Okay, so I'm going to separate these two and bring sine x, okay, over, and this x over, so, oops, sorry, x right here. So we know this one has a limit as x approaching 0. And how about secant cubic, secant x to the power 3? Well, for those of you who are not familiar with secant, we can write secant x as 1 over cosine to the power 3 x. Okay, well, x approaching 0 is just a direct substitution. And this piece has a limit, so we can apply limit law. Okay, we can apply limit law. Applying limit law meaning that we're going to take limit separately. So you just have to write it separately. Okay. The former is a direct substitution. That's going to be 1 over 3. Oops, sorry. 1 over 3 multiply. Okay, I'm going to write it here. Cosine to the power 3 of 0. Cosine 0 equals to 1, right? And the derivative, the limit of this piece is just equals to 1. So finally, the limit is a third. Okay, I just mentioned that you could have taken derivative. You could have continued to take a derivative after this step. You certainly could. Okay. You certainly can do that. If you do that, okay, I wouldn't be surprised. Some of you may like to go that. It's just that you're gonna have to use a product rule. Okay. So what you can do is that you can say, I'm gonna take a derivative one more time here using L'Hopital rule. Okay. So I'm gonna write or another way. So in this case, what we did here is we use L'Hopital rule twice, and then we changed the strategy, right? Suppose we use L'Hopital rule like more than 3 times. Okay, we're gonna use L'Hopital rule 3 times, right? So we use L'Hopital rule the first time, we use L'Hopital rule second time, and you want to continue to use L'Hopital rule because if you want to continue to use L'Hopital rule, yes, you can. And what are we getting? We are getting, so let me reorganize this term, okay? So this is secant squared, all right? The 2, right, I'm going to reduce it with the 6, sorry, right? So basically, I'm going to take a derivative. So this is 3x, right? So let's just get rid of this. And you can take the 1/3 outside, okay? Outside the fraction. So I'm going to bring the 1/3 outside. So I'm only going to apply L'Hopital rule on this piece. Okay, I'm only going to apply L'Hopital rule on this piece. So this is the first time. Second time, I'm going to use it the third time. On the third time, I'm leaving the third outside. Okay, I'm applying L'Hopital rule on this piece. And of course, you can see the derivative of x equals to 1. The derivative of secant squared, we're going to have to use a product rule. Okay, so think out loud. You can do it directly. You can do it directly, but I just want to take this opportunity to review with you how to take a derivative of this product. So we're basically using product rule, okay? And we're gonna differentiate that part. And we're gonna differentiate the tangent to see what happens. All right. So you get it gets a little bit more work here, but you know the work was not finished. So either way, you can do this way. I'm just showing you you can do it this way. There's more than one way to work this question out. So on this piece, we're gonna have to do chain rule, right? 2 times secant x, and then derivative of secant x is secant x times tangent x plus secant square x and multiply the derivative tangent. The derivative tangent is secant squared. Okay? So this will be the result you're going to put on top of here. And that's not a problem. It's great. It works. Okay? So then on the next step, what we are getting is that the denominator 1 can be omitted. So we're going to put the whole thing like this. And that's just a direct substitution. That's going to be a direct substitution. Okay, because all of these trig functions, they are um, they're all defined and continuous, right? The secant to the power 2 times secant to the power 2, and that's going to be secant to the power 4, right? So secant times secant, that's going to be secant squared. Not a problem at all. Okay, so I'm going to just bring this one here. Okay. And direct substitution, we're going to replace x by 0, 0. All right. Secant squared, secant 0 is 1. Tangent 0 is 0. Secant 0 is 1. So in the end, we still get 1/3. So either way, you can do it either way. Either way. However, after the third time we use the L'Hopital rule how many times? Once, twice, 3 times. Well, after we've done the third time, we can no longer use it because there won't be any, there's not a denominator as of now, okay? All right. Well, the denominator equals to 1. I should not be saying there's no denominator. Denominator was 1, okay? So 1 does not approach 0, does not approach infinity, so L'Hopital rule does not apply. Okay, you can see we have a lot of tools at our, disposal. The next one, I think, is going to be example number 5. Example number 5. Example number 5 here. Okay. And there's a possibility we might be using L'Hopital rule, right? We are in the section of studying L'Hopital rule after all, so we're going to put it here. And, feel free to use our scratch paper. Feel free to use our scratch paper. When x is approaching pi, okay, from smaller than pi, okay, when x is approaching pi from smaller than pi, cosine approaches cosine. I have a little doubt whether I copied the question correctly. Okay, let me just double check. Well, let me just double check. I think when I was writing it down the first time, I did double check. And I think I did have the question correct. But for some reason, this one, excuse me. Well, x is approaching pi. the numerator is approaching sine pi. Sine pi is 0. 1 minus cosine pi. Cosine pi is -1. Okay? So this limit is a direct substitution. We don't need to use L'Hopital rule. Okay, and also L'Hopital rule does not apply. Okay, L'Hopital rule does not apply. So it's a direct substitution. We're going to replace x by pi, cosine by pi. Okay, and so you can't just get whatever limit here and then you just take derivative. No, you have to check the conditions. Okay, you have to check the conditions. So this one is a direct substitution. It is a direct substitution. Okay. I actually did not find the question, but it doesn't matter. It doesn't matter. So we got it. So sine pi is 0. 1 minus cosine pi. Cosine pi is -1. The denominator you can see is not 0. But in the end, of course, it's a 0. In the end, it's a 0. Okay, so this example will be is a good reminder that for us, not just you look at the limit, you start taking derivative without checking the condition. We must check conditions first. Okay, we must check the conditions first. Okay. All right. So let's look at example number 6. So example number 6. Here we go. Maybe we get to use L'Hopital rule. Okay, so we put the L'Hopital rule right here. And let's observe this limit. When x is approaching 0 from larger than 0, ln x is approaching -infinity. Okay, so let me think out loud in case you guys still need some more refreshing. Think out aloud. When x is approaching 0, ln x, when x is approaching 0 from larger than 0, ln x is approaching -infinity. Okay. The reason is that, of course, you know the curve. You can easily graph the curve of this function. All right. So this is the function we must be very familiar with. So when this function is mentioned, you know that when x is approaching 0, okay, the domain is x greater than 0. When x is approaching 0 from larger than 0, and the y values, ln x is approaching -infinity. Okay, so this is the function we must be familiar with. I hope that that's already in your mind. All right, so let me clean up. Okay, so with that picture in our mind, okay, now is you also see it physically, and I hope that you can use these knowledge freely. Okay, but when x is approaching 0, x is approaching 0. So we basically have a situation, that is 0, it's a 0 multiply infinity situation. Well, 0 multiply infinity, is it 0? Is 0 multiplied infinity 0? We have seen plenty of those situations that it's not necessarily true, right? But what do we do in this case? Well, this is what we can do. Number one, we cannot use L'Hopital rule. We cannot use L'Hopital rule. Okay, because we don't have first of all, we don't have a fraction situation, right? We must have a numerator denominator situation. Okay, so I'm going to put it here, right? We don't have that. We don't have this situation. So can we create one? Yes, we can. Okay, because there's no other elementary method we can use. What we can do is that we can make ln x over 1 over x. So we create a complex function. We create a complex function. And then what we got? Now, as x approaching 0 from larger than 0, ln x approaching negative infinity, 1 over x as x approaching 0 from larger than 0, 1 over x approaches a positive infinity. So we have an infinity divided by infinity situation. Okay, infinity over infinity. So we can now apply L'Hopital rule to the numerator, which is ln x. The denominator would be 1 over x. So derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. All right? And reduce it. How do we reduce it? How do we reduce this? Well, you just multiply the top by x squared and multiply the bottom by x squared, which is the common denominator. Okay? So on the next step, and this piece is x, and this piece is just negative 1. When x is approaching 0, it's a direct substitution, so it's going to be a 0. Okay? It's going to be a 0. All right. All of the thinking out aloud or the pictures, they're not necessary to show to the reader. You just have to show this much will work. You just have to show this much will work. Okay? All right. So that was example number 6. Let's get to example number 7. Example number 7. And where's our L'Hopital rule? L'Hopital rule, we bring it with us. Okay. Well, in this case, for sure, we cannot use L'Hopital rule. It's not a dividing situation, right? It's not a, f divided by g. It's a when x approaching 1, ln x is approaching 0. So 1 over 0 is approaching infinity. X approaching 1, 1 over x minus 1 is also approaching infinity. So infinity subtract infinity. We have a situation of infinity minus infinity. Okay, so that's the indeterminate form. And we cannot apply L'Hopital rule because L'Hopital rule is either 0 divided by 0 or infinity divided by infinity, right? So either one of these two forms. So what do we do? Can we use any other elementary method? Doesn't seem to be easy. Okay, so let's create a quotient situation. All right, let's create a quotient situation by finding the common denominator to make it into a one fraction form. Okay, so the common denominator would be x minus 1 times ln x, right? So over here, so it's going to be x minus 1 minus ln x. Okay, the common denominator, right, is x minus 1 ln x. All right, so if you need to pause and to figure out why this is the case, you may, okay? We don't need the big parentheses outside. So when x approaching 1 from larger than 1, denominator approaching 0, numerator is also approaching 0. So we can actually apply L'Hopital rule now. L'Hopital rule. Differentiate the top. Okay, so we take a derivative of x minus 1 minus ln x. Derivative of x equals 1. The derivative of 1 is 0. The derivative of ln x is 1 over x. The denominator, how do we find the derivative of the denominator? Well, product rule. Product rule, we treat it as this number multiplied the other one. We can call this is f, this is g, right? So we're gonna do, you wanna do it inside the case. So that's gonna be this piece plus that piece, right? So derivative, we're applying product rule. Okay, you can skip that step actually. Okay, you can just write down this step directly. The derivative of x minus 1 is 1, right? 1 can be omitted. The derivative of ln x is 1 over x. 1 over x. All right? So what do we get now? What do we get now? All right? Can we simplify this a little bit? Can we simplify this a little bit? Right? We certainly can. We certainly can. Okay? We're going to multiply x on the top. I'm going to multiply the x in the bottom. Right? So what do we get is that this x times 1, and that's going to be x, and x times 1 minus x, that's going to be a 1. So this x is gone. And this x, you're going to multiply this piece, so we're going to get x times that, and this x times the whole piece here, we're going to get just x minus 1. Okay, so this is gone. So this whole thing is gone, and we can remove this x minus 1. All right. What else can we do here? It looks like there's not a very obvious elementary method at our disposal. Can we apply L'Hopital rule one more time? Okay, naturally we'll think that way. When x approaching 1 from larger than 1, the top is approaching 0. And this is going to be approaching 0, this approaching 0, so the entire bottom approaching 0. Yes, we can apply L'Hopital rule one more time. How many times we're applying L'Hopital rule? 3 times already, right? So the derivative of the top, x minus 1, is just a 1. The derivative of x times ln x, we're going to have to apply product rule. Okay, so we're going to first differentiate. So we're going to differentiate that piece. Okay, so let me just show you here. Okay, this is a product rule. This is a product rule. So x prime, ln x prime, and then we're going to differentiate x minus 1, right? X minus 1 being differentiated is equal to 1. Applying product rules, the derivative of x is 1, and the derivative of ln x is 1 over x. So look, we have applied, L'Hopital rule the first time, L'Hopital rule the second time. I'm sorry, we didn't do it the third time. We did not do it the third time. Okay, my bad. We did it the second time. And we got these. This is 1. 1 plus 1 is 2. That's what we got. We can no longer apply L'Hopital rule because the numerator is neither 0 nor infinity. And can we do direct substitution? Yes, we can do direct substitution because the function is a continuous one at 1. So we get ln1 plus 2. ln1 is equal to 0. So we get 0 plus 2. The final answer is going to be 1/2. Wait a second. Wait a second. We have started with infinity subtract infinity, right? When x approaching 1. So the limit of infinity subtract infinity, what is the limit? Certainly not 0 here. It's 1/2. Okay. All right. So let's look at that will be example number 8. Example number 8 is worth noting because this question, okay, so I'm gonna let me get started to explain it to you. Okay, let's get started to explain it to you. First of all, we cannot apply L'Hopital rule directly, and there's not an obvious elementary method to explain. And the situation we have here as x approaching infinity is the infinity subtract infinity. Infinity subtract infinity, we don't know what we're gonna get. Okay, anything is possible. So we want to transform it into something more certain. Whether we apply L'Hopital rule or not, but we want to transform to something more certain. How do we transform it? How do we transform it? So in this case, what we do is that we're going to factor it out. We're going to factor it out. First of all, limit law does not apply. L'Hopital rule does not apply. We're going to factor out x. Okay? So inside, we're going to have e to the power x divided by x minus 1. Okay? If you distribute x back, to the parentheses, you'll get back to where we started. Okay, so this is the right factorization. So after this factorization, what do we do? If we make a common denominator, right? So this 1 will become x under x. And we are getting the next one would be, we keep the same denominator, numerator, subtract numerator. So we got something like this. So we basically have this form, x multiply something like that. E to the power x minus x divided by x. Okay? But what would this be? What would be the limit of this piece? Right? What would be the limit of this piece? Now we have, x approaching infinity, this is approaching, x is certainly approaching infinity, but how about this piece? Okay, we can check. What we can do is we can check a condition. Okay, we can check this piece. Okay, we're not taking limits separately. We just look at these two functions, right? This piece, we know it approaches infinity. How about this piece? When we look at this limit, what do? We can apply L'Hopital rule because the numerator, when x is approaching infinity, e to the power x minus x is going to be approaching infinity. Denominator is also approaching infinity, so we can take a derivative of the top. which is going to be e to the power x over 1, e to the power x minus 1. The denominator would be just 1. So this whole thing is going to be infinity. Well, how can we be certain that e to the power x minus x is going to be infinity, right? How can we be certain? Because this is exponential functions. The other way you can tell is that you can tell from this picture. Okay, from this picture. This is the graph of e to the power x, right? These graphs can be used this way, right? As x approaching infinity, you can see this side, right? As x approaching infinity, you can see e to the power x minus x is getting higher and higher. So this piece, e to the power x minus x, does approach infinity indeed. Right, so I know all of these considerations. It's a lot of information. It's a lot of information. And therefore, we can use L'Hopital rule, right? So here, we have come to this point that the limit of our interest has become the limit of something approaching infinity, and the other piece also approaches infinity. So infinity multiply infinity is surely going to be infinity. Infinity minus infinity, we don't know. But infinity multiply infinity is surely infinity. All right? So now, after this example, let's look at another one. This will be example number 9. Okay, example number 9. This is going to be another situation. Okay, we're going to put it here. And we're going to bring our L'Hopital rule with us. Okay, so this indeterminate form, okay, why we call it, well, we call it indeterminate form because at once x approaching 1, sine 4x is approaching sine of, wait, I think this is a 0. I think this is a 0. Okay, let me double check. I was right. So this is approaching 0. Okay, my bad. Because if it's not, it would not be an indeterminate form. Okay, we will not need to work it the way we do. Okay. As x approaching 0, we have 1 plus sine of 0, right? Well, x approaching 0, sine of 4x approaching 0. So this is 1 plus 0. It's 1. So this well, for cotangent, cotangent 0 is 1 cotangent. Just in case you guys are not familiar with a cotangent. Okay, so let me write it down for you. Okay, so think out aloud. Excuse me. Okay, cotangent. Cotangent x is equals to cosine x divided by sine x. Okay. When the domain of cotangent does not include a 0. In other words, when x is approaching 0 from larger than 0, Well, x is approaching 0 from larger than 0, sine x is approaching 0 from larger than 0. Okay, if you look at the sine curve, in the neighborhood of 0, I'm going to show you a couple pictures to get you more, at least review of those trig functions, right? You see, if you don't know enough about cotangent, or you have limited knowledge in trigonometry, so here at least you know sine curve, right? Sine curve look like this. Sine curve look like this. Okay, you can get it at your fingertips. Okay, I think your iPhone probably does that for you. And cosine x. Okay, cosine x, the curve for cosine x. There we go. There we go. All right. So I'll get them to line up. I'll get them to line up. All right. There we go. All right. Make it a little wider, narrow, well, I'll try to put them on the same screen, okay? Sine x, when x is approaching 0 from larger than 0, what does that mean? When sine, okay? When x is approaching 0 from larger than 0 for sine and for cosine, okay? When x is approaching 0, right? Cotangent equal cosine divided by sine. So the denominator is approaching 0 from larger than 0. The numerator is approaching +1. So the numerator is a positive, denominator is a positive. So this piece, right? Cotangent at when x is approaching 0 from larger than 0, cotangent approaches positive infinity. Approaches positive infinity. Okay, this is how you can use the basic graphs of sine and cosine. But if you have a little familiarity of a cotangent, you can also see that by graphing the cotangent curve. Okay. Here I'm just using minimal. Hopefully we can use minimal knowledge about trig functions, just sine, cosine. We can resolve this issue that involve cotangent. Okay. All right. So without further ado, all right. So we know that cotangent approaches positive infinity, and what's inside the parentheses approaches 1. So we have a situation of, this is the indeterminate form of x raised to 1 to the power of infinity form. What do we do with this kind of form? Well, we use logarithm. Okay, so all these think out loud. Okay, you can just put it on the side. We're going to assume y equals to the whole piece without the limit. Okay, without the limit. And then we're going to take a logarithm on both sides. Ln on both sides. Power rule, we got cotangent x multiply ln the whole of the parentheses. All right. So then what do we do? Now we're going to take limit on both sides. The left-hand side is this ln y, but the right-hand side, we want to create a quotient form, because we might be using L'Hopital rule, right? We might be using L'Hopital rule. So how do we create that quotient form. And here we go. We know that cotangent is the reciprocal of tangent. Okay, so this will be our numerator. Okay. And so cotangent is reciprocal is 1 over tangent. It's 1 over tangent. So tangent will go here. So now we have a quotient form. We have a quotient form on the right-hand side. And in particular, when x is approaching 0, from larger than 0, we take limit on both sides. The top is approaching 0. The bottom is also approaching 0. Okay? Tangent 0 equals to sine 0 over cosine 0. So it's approaching 0. So we can apply L'Hopital rule. We can apply L'Hopital rule. That's great news. That's great news. All right. So now, applying L'Hopital rule, we're going to take a derivative of the top. The derivative of the top, we're going to be using chain rule. Okay, so first is 1 over 1 plus sine of 4x, right? And then we're going to differentiate 1 plus sine 4x. The derivative of 1 is 0. The derivative of sine 4x is a cosine 4x. And then we're going to differentiate 4x, which is going to be 4. Okay, so we use the chain rule on ln x. Okay, so think out aloud. Okay, so derivative of the top. Okay, derivative of the top is a chain rule. Chain rule. Okay, chain rule. So differentiate ln, which is 1 over the bologna, right? And we differentiate the bologna, which is derivative 1 is equals 0, derivative sine 4x is a cosine 4x. And then you have to differentiate 4x, which is going to be 4, right? So that's how we use the chain rule to differentiate the top. Differentiating the bottom, we get secant squared of x. Okay, so now simplify. Simplify Simplify, we're going to bring the 4 over here, right? Cosine 4x to stay where it is. And we can, bring this guy under, right? We're going to bring this guy under. There. So this is just before. Those are just before. All right? So x approaching 0. And then what? How do we find the limit, right? This still looks pretty complicated. We may be thinking, do we need to use L'Hopital rule one more time? Do we need to use L'Hopital rule one more time? Well, when x is approaching 0, 4x approaching 0, cosine 0 is, cosine 0 is 1. So we cannot apply L'Hopital rule. Can we do direct substitution? Maybe, yeah. Because secant 0 is 1. Sine 4 times 0 is 0. So we can do direct substitution. Sorry. Okay. So we are going to be doing direct substitution. When we do direct substitution, we're going to drop the limit, substitute the x by 0, substitute x by 0, substitute x by 0. And sorry, we remove that dot. What do we get? The top the top is equals to 4 because cosine 4 times 0 is cosine 0. Cosine 0 is 1. Secant 0 is 1. Inside the parentheses, 1 plus 0. So the total, the final answer is a 4. Okay? So what we got is that we got the derivative of ln y equals to 4. But that's not what we wanted. We want the limit, I'm sorry, the limit of ln y is 4. We want the limit of y, right? So what we really wanted is y. So how do we get to the limit of y? So we're going to be doing the following steps. Okay? We know this is what we wanted. Okay? This is what we wanted. And this is really what, this whole thing is really y, right? And how is y related to ln y? Well, how is y related to ln y? Well, y is related to ln y by e raised to the power of ln y. Okay? All right? So now, because e to the power x is a continuous function, so this limit can go across the continuous function. So e raised to the power of ln y, we can bring that limit. We can bring that limit across to the top because e is a continuous function. And finally, we get e to the power of. So we're going to use the result we got here, right? Which is here. And that's going to be e raised to the power of 4. All right. That was a long one. So let's recap what we did. Okay, so let's recap what we did. We started out with the limits to be found. And we have the indeterminate form, 1 to the power of infinity. We don't know what that is. So we use logarithm. So y, we assume y equals to the whole of the part without taking limit, and then we take ln y, and then we take limit of ln y. And it turned out we can use L'Hopital rule. So after using L'Hopital rule, we found the limit of ln y as x approaching 0. And then we use a relationship between y is equals to e to the power ln y. So this is a key relationship we use, okay? Which is y is equals to e to the power of ln y. So this is the key relationship we used. Okay, we use this key relationship here. And that's it, right? And we also used the continuous property of the continuous function, e to the power of x. E to the power of x is continuous, therefore the limit can go across it, right? We have that derivative, we have learned that property some time ago. So let me just make sure you know what I'm talking about. Okay, so this step, right, take the limit from outside inside, is this property. Limit, I'm sorry, let me redo it. Okay, limit 1 x is approaching a, okay, F composite G of X equals to F of limit of G of X. So if F is continuous, this limit, right, that taken outside can be taken inside, or taken inside can be taken outside. Okay, so this is the property we learned before the midterm. All right. Oh gosh, what time is it? What time is it? I don't think we can do all of it. That would be too long a lesson. This next question actually is similar. I'm going to leave it to you. Let's see. Okay. Let me look through what we have in what's coming next. What's coming next? Maybe we'll have to do another lesson if necessary. Let's do this one anyway, though. So this is going to make example number 9. Okay. Example number 9, because I saw that the following questions are not that difficult. Okay. So number 9. Okay, for example, this one you just directly use, L'Hopital rule. So I'm going to leave them for you. Let's do this one. Okay, so this is what kind of form is this? This kind of form is this. This is as x approaching 0. So we basically have a 0 to the power of 0. It's an indeterminate form, 0 to the power of 0. What does that equal to? Well, then you say equals to 1. No, that's wrong. Okay? Then you say, isn't that true that so let me put it here. This is the indeterminate form, but I'm gonna think out in my think out loud part. I do want to mention a couple of facts that some of you probably remember that x raised to the power 0 is equals to 1. But this is conditional, okay? X raised to the power equals to 1, x cannot be 0. X cannot be 0, okay? Go back to look at your algebra book. These two are together, okay? Then you say, what's 0 to the power 0? It's indeterminate. It's indeterminate, okay? So we're gonna handle this with the same technique. So we're gonna let y equals to x raised to the power x, and we take ln y on both sides. So we're gonna have ln x to the power x, and by product, oh sorry, this is going to be power rule of logarithm. Sorry, okay, power rule of logarithm, and then we're going to take limit of ln y on both sides. Okay, to take limit on both sides. So we're going to take limit of ln x times ln x. When x approaching 0, ln x approaching negative infinity, but x approaching 0. So this we cannot use L'Hopital rule. But we did a question similar earlier. Okay, we did a question similar earlier. Let me show you. X raised x, this one. Okay, this one. Remember how we did there? Okay, so we're going to bring it here. So this is going to be exactly what we're going to do. Okay, right here, right? So basically we're going to copy this part. Exactly the same question, right? So we're going to apply all of these. We just copy and paste. Just copy and paste. Okay, we apply L'Hopital rule a couple of times. Okay, we apply L'Hopital rule once. Yeah, we apply L'Hopital rule only once, and then we reduced it. Okay, we got 0. So this limit, the limit as x approaching 0 from larger than 0 is equals to 0. But once again, that's not what we wanted, right? We wanted the limit as we want to limit this piece is y, right? We use that relationship one more time, which we did earlier, this relationship, right? So we use this relationship one more time. So we replace it, right, by that. And then by continuity of e to the power x, so that's going to be e raised to the power of limit of ln y. I think the writing, it looks a bit weird. Okay, so let me rewrite it. Let me rewrite it. Power, oh, you know what? Maybe I should rewrite it this way. No. Let me rewrite it to see if that will make it better. It should be in the power. Okay, it should be in the power. So ln y. All right. That's the best the software can do. So e to the power 0. And e to the power 0 is equals 1. All right. So that makes it the last question for this clip. Thank you for watching. If you have any questions, please don't hesitate to reach out to me. Thank you.